Ladies and gentlemen, a very warm welcome to all of you here to my session about persistent memory in operation. My name is Dieter Kasper. I'm with Fujitsu for more than 30 years now. I'm CTO of Enterprise Platform Services. EPS is responsible for all the mainframe business of Fujitsu in Europe. Please allow me to start with a couple of statements about Fujitsu. Fujitsu is clearly the #1 IT company in the Japanese market. In 2015 there was a rating from Gartner about the worldwide IT service provider, and this ranking Fujitsu was ranked on #5. The vision of Fujitsu, it's about human-centric computing, which means we are trying to put the people in the center of our interests, in the center of our offering from the product, solution and service side. And we are trying to contribute to create a better future, a more prosperous and a more happy society. We have employees around the world in order to be able to serve our customers worldwide with focus areas in Japan, Europe, Asia and in the Americas. I would like to start with a short introduction about the technology of persistent memory, and I'm pretty sure all of you are aware of this pyramid. On the top we have the memory, down to the storage with fast access. On the top, small capacity, and at the bottom, high capacity and slower access. And in the middle you can really see this world is divided into two pieces, the upper and the lower part. And in the upper part we have volatile attributes with byte access directly from the CPU, and below this border we have I/O in combination with persistency. And now with the advent of persistent memory, all of a sudden this combination is broken and we have byte access in combination with persistency. Directly, the CPU can directly access the storage without any I/O in between. And also, in the past, there was a significant difference from a latency perspective between the memory world and the storage world, round about an order of magnitude of 5. And yes, with the advent of the SSD device, this shrink a little bit, maybe to the order of magnitude of 4 or maybe down to 10,000, but still this is an enormous difference. And here with persistent memory we have only around about a factor of 10 difference between the persistent memory and DRAM. So yesterday, 10 o'clock Pacific time, there was an announcement from Intel about the new Cascade Lake CPU and also about this new OPTANE persistent memory. OPTANE is the brand name from Intel for their technology based on 3D crosspoint, and OPTANE is available as a storage device through the PCIe bus with I/Os, and will also be available as OPTANE Data Center Persistent Memory Module of the name. So the abbreviation would be DCPMM. As you can see, this is a DIMM which will fit in every server which is able to host a Cascade Lake CPU with also DRAM modules. The available capacities will be 128, 256 up to 512 gigabytes. As you can see, behind the memory controller there will be the, let's say, the regular DRAM as well as the DCPMM with the OPTANE module, and the OPTANE controller will ensure that the operating system doesn't have to take care of wear leveling. The controller on top of the module will ensure that this module will do its job at least for 5 years. As I already said, latency-wise, here on the left-hand side you see the bar for a typical access to a NAND SSD, and the blue color is representing the latency which is coming from the media. And the smaller part, the green part at the bottom, this is the portion which comes from the software stack, and in this case this is already the optimized NVMe software stack, not the old heavy-weighted SCSI stack. And on the right hand side with DCPMM the latency is shrink to almost an invisible bar, and the statement, and by the way the slides, I grabbed the slides from the persistent memory summit. You can see all on every page the link where I grabbed this information, and here the Intel colleague stated that it's expected for a 64-byte access that the idle latency is somewhere between 100 nanosecond and 350 nanosecond. This technology can be used in two different modes. The first mode is called up direct, which means the application can directly access the persistent memory. So from an operating system perspective, the operating system will see the regular system memory, which comes from the DRAM, and a second memory class, the persistent memory provided by the different DCPMM modules. The second mode is called memory mode, and if you remember, the huge capacity which is now available with these modules, 512 gigabyte, half a terabyte per DIMM, so a 2-socket machine can be equipped up to 6 terabyte capacity. So in some cases the application will say, well, I don't care about the persistency attribute, just give me this memory, and therefore you can configure these modules in a memory mode, and in such a mode the total capacity of the DCPMM will be provided as system memory to the operating system, and the capacity of the DRAM modules in your system will be invisible, and the hardware subsystem will use the DRAM as a sort of level 4 cache in front of the DCPMM modules in order to ensure performance which is very close to a pure DRAM configuration. And of course you can also mix these modes. So for example, you can say, well, from the 6 terabytes I wanted to use 2/3 of the capacity for memory mode and the rest for the up-direct mode. And also during the Persistent Memory Summit in January this year, there was a use case shown with the HANA database. So HANA is already ready to support these persistent memory supports, and there will also be a talk tomorrow, the 1457. So if you're interested in this use case, please have a look and join this breakout session. So the key attributes of the persistent memory, this is really the small difference between DRAM and persistency, and I think this attribute can really bring us to a game changer how we design and how we develop operating system as well as application. For all of us, for the last 4 decades, we have always to think about the memory. This is fast, and if I want to store something, I have to consider that it's slow. I have to group my information and store it from time to time. And now with the persistent memory, you're just operating persistent memory, and your data will stay persistent. So this will enable us a complete different thinking, a complete different design of applications. Well, maybe some of you might argue persistent memory, this is not really something new. NVDIMMs, non-volatile DIMMs, have been around quite a couple of years. Yes, this is true, but there are at least 3 main differences. So as you have seen, here the capacity is enormous large, whereas the old NVDIMMs, they had only a small capacity of 4, maybe 8 gigabytes, so less than the DRAM modules. They were extremely expensive, and the old modules based on DDR3, they were really, you can only use them with a proprietary motherboards. And here with these DIMMs, they are following the JEDEC standard, so every x86 motherboard which can host a Cascade Lake can also be equipped with this persistent memory modules. From Linux kernel 4.4, this technology is supported as well as from the Microsoft operating system 2016. And yeah, I think this can enable us to dramatically increase the overall system performance and also the individual the use cases, one thing at the top is called execute in place. So if you think today, if you have an executable, if you want to run this executable, you have to load it from the disk drive into the main memory. Once it is loaded in the main memory, then you can jump at the beginning and execute it. In case of persistent memory, it will stay already in the memory, so there's no need for loading it. You just execute it in the place where it's sitting. So this is the execute in place, and of course this is also true for libraries, whether they are on the user land or kernel object or the kernel itself. Other use cases will be the in-memory database as well as the traditional databases with its journal enterprise storage, where libpmem can act as a caching, or it could be used to store the metadata of the traditional file systems, as well as can be used in high performance computing or analytics or in AI. So after this short introduction about the technology, how do we set up and configure the stuff? So there are basically two new commands introduced to configure this. The IPM control, the former name was IXPDIMM, and the second tool is called ND control. So IPM control takes care for the more lower level configuration stuff, and ND control for the upper level stuff. And because it is through memory, it will also show up in the memory map echo 820. If you have legacy application, yes, there is also the options to put in between lock logic again, which will provide you an atomic center logic. So all traditional file systems with all the traditional legacy application on top can make use of this new technology and can also benefit from the higher performance. But if you would really like to take the best advantage out of it, you have to use this file systems with the so-called DAX mode, so direct access and execute in place, and this DAX mode is already implemented for the extended 4 file system as well as for the XFS. So these are the configuration tools, and again I grabbed this page from the System Memory Summit. In the middle you can see a couple of benchmark tools, the MLC, the memory latency checker. From Intel, it's free, but it's only provided in a binary format. The well-known FIO, as well as the PMEM bench, which is included in the PMDK Git repository. And on the analysis side, a couple of tools from Intel. Some of them are part of their Intel Studio compiler suite. Okay, so now we have these persistent devices in our system, and similar to the hard disk drive, we have to make up our mind how do we want to use them. In case of a hard disk, we have also to make the decision, do we want to use each hard disk as a single device and then take care about load balancing and memory management to fill them up equally, or do we want to run a stripe across these devices, which will give us a large capacity pool where we don't have to take care about the load balancing and the capacity balancing. So there are two modes possible, an interleaved mode between multiple DIMMs or a non-interleaved mode. And once you have defined this mode, you will get these gray boxes. The gray boxes are called regions, and then on top of the regions you can define namespaces. And once you have defined namespaces, so you have the modules, the region, the namespaces, and then on top of the namespaces you can build your file system, and then on top of the file system you will get files, and the files are representing memory pools showing up as memory mapped files, and the memory mapped files, they can be used from different applications or threads, as you know this already from the traditional nmem logic. So the only difference is With nmem in the past there was an invisible I/O below, and here with this new nmem logic, this is a true direct access to the media. If you look up the internet about this app direct and memory mode, you might also this is the important thing is missing. So there is an abbreviation called 1LM and 2LM, so 1 level memory, 2 level memory. So the 1LM it's the app direct, and the 2LM it's the memory mode. So this is the projector, it cuts off the portion on the left hand side. So the steps to enable the devices is, of course, the BIOS has to detect the modules, then you have to make up your mind between app direct and memory mode. You will define application goals, which results in implicit regions and then namespaces, and as we have learned, there are a couple of tools to manage this. The gray boxes, this is possible to do so, and in our cooperation with SUSE in last autumn, I think Hans, you had boards from Intel, and at the beginning you were using the UEFI shell for all the commands, and we were more focusing on the green boxes, so the BIOS for the hardware detection, the IPM control to define the goals, and the ND control to define the namespaces. So this is the system in more detail which I used. It's a PRIMERGY server, a 2-socket system, so we have the 2 CPUs. And as you can see, each CPU has 2 integrated memory controllers. Each controller has 3 channels, and behind each channel you can put 2 DIMMs in the channel. And if you want to put a DCPMM DIMM inside, it has to be put into the slot closest to the CPU. So in both slots you can put DRAMs, but if you want to use a DCPMM, it has to be populated here in this slot close to the CPU. And there are also strict rules how to start the population. So first of all, you start with the first CPU, first memory controller, first channel, then second memory controller, first channel, then you go to the second CPU, first memory controller, first channel, and so on. So number 5 would be this slot here. And the blue boxes here, they are symbolizing my target configuration. I want to create a couple of namespaces on 2 DCPMM modules which are in a stripe set, which are running in an interleaved mode, and the second one is standalone, and I also will create a namespace on DRAM just for comparison later. Okay, so here is the example, some example commands, so you can tell the system, show me the DIMMs. So in my system you will see I have 4 DIMMs, one of them unfortunately is not functional. They have close to 256 gigabyte capacity. A small capacity is needed for internal management of the OPTANE controller. If you show topology, you will not only see the non-volatile devices, but also the DRAMs. You can see the location, where are they sitting in the system. For a moment, let's remember this physical ID here. And you can also use the ND control to look at the DIMMs. And here again you will see this physical ID from the command before, where we had this mapping to the physical location in the server. And here also device names are showing up. These are character devices controlled by the DIMM control device driver. And another interesting thing is here the ND control has a different syntax than the IPM control. ND control uses --DIMM. The IPM control, uses only 1 -DIMM. So for me, it seems to be that there was at least 2 different groups not talking very much to each other to keep the same syntax to make it more easy for us. Okay, so we have now seen where the DIMMs are sitting. Now we are going to create a goal. You see here the syntax about this goal. You can define the capacity, on which socket you want to define this goal, and important, the persistent memory type, interleaved, non-interleaved, and also the memory mode as a percentage. So as default, it's 0%, and in my use cases, which we will see on the next couple of slides, because I did not use the memory mode at all. So I create a goal across two DIMMs. It is app direct, you see the capacity, and after the command, the command says a reboot is required. And now you can imagine why is it called goal, because it's a goal where the BIOS has to fulfill this wish, and after a reboot, the system comes up again, and I ask the system, please show me the region. Then you will see that the region was created, the gray box before, and here we have one region with the 500 gigabyte, the two modules, and the second one which I created with an extra command, which is a non-interleaved, it's only the single module. You can also see the stripe set with this PCD config, interleaved about two modules, and the second one, this is just a standalone module here. Okay, now we have the region. Let's create a namespace on top. Again, a couple of flags here. The most interesting one is the mode. And if you want to put a DAX file system on top, you have to use the mode fsDAX, which you can see here. So I'm putting it on the region 0, fsDAX, and here in the example I'm not using the total capacity but only 480 gigabytes here. On the right hand side you can see the region 0 with the two DIMMs here, the nmem 1 device and then 0, the region 1 with the single module here, and I also created regions on DRAM, 50 gigabytes, and here therefore the persistency domain is unknown. On the other page you probably have seen it says memory controller, and this region which is sitting on DRAM has the block device PMEM 3, and how can this be achieved? Well, during the boot sequence, as a boot parameter to the kernel, if you put in mmap, and the logic is give me 50 gigabytes of a region with the offset 4 gigabyte, and here I said please give me a second one with 50 gigabyte, and this will show up in the memory table later as a type 12. So here on the next page we have this E820 map. As you can see, the persistent memory has the type 7. So this is the BIOS map, and later on from a system perspective you can see the type 12, which comes from this emulated namespace which is sitting on DRAM. So we have the three devices, PMEM 0, 1 and 2. We create a file system on all of them. We mount the file system, and in the mount we are putting the DAX option in there, and we can check it with the single mount command. Yes, all these three file systems are mounted with the DAX option here, and also the df command. The output is shown as you know it from other file systems. So the 0, this is my 450 gigabyte, this is the single DIMM, instead this is the 50 gigabyte DRAM here. Okay, so this was the setup, and the next question is, if we have set it up, how can we use it from a programming perspective? And therefore I want to take a short look onto the programming stack. A couple of years ago, Intel started to create this ecosystem, and it groups around several operating system vendors as well as companies offering applications or cloud stacks. And this year, the Storage Networking Industry Association was heavily working on the so-called nmem programming model, and the two boxes on the right-hand side, they took care about the NVMe interface. This was introduced starting with Linux kernel 3.1 and almost completed with 3.15. And the two boxes on the left-hand side, kernel and userland, they take care about the persistent memory. So if you remember my statements at the beginning where I said, well, in the past, with the legacy access, with the I/O, the yellow portion in the middle, if you want to ensure consistency from the application side, you have to be aware that there is a buffer cache in between the Linux operating system where you have to flush the data to ensure that the data is really stored and sitting on the persistency layer. So at the moment you may think, well, with this app direct, with this direct access of the CPU, this is nice, I'm getting rid of all this handling of the cache logic. But unfortunately this is not true, because we don't have the cache in the operating system, but we have the cache in the CPU. So here as an example, a CPU with 4 cores, we have the level 1 cache for the execution as well as for the data, the L2, L3 memory controller, and the persistent memory DIMMs at the bottom. And today, if you're running your application in DRAM, you really don't care if you write a value into an address field, whether the data is sitting in L1, L2, L3 in the memory controller or the DRAM itself, because on a power loss you will lose the data anyhow. But now, if you are using the system memory behind, of course you have an interest that the data is stored in this layer and not sitting somewhere in between. And to control this, Intel has introduced a couple of new CPU commands, the cache line flush optimize, and cache line write back. So the flush means it's a move command. Afterwards the data will be invalid in the cache, whereas the cache line write back, it's more a copy, it will still sit in the cache. And once the data is in the memory controller, so all these commands will ensure that the data is flushed into the memory controller, and now from the memory controller it's up to the board design to ensure that ADR, asynchronous DRAM refresh, is enabled on these boards. So in a power failure, the power supply is powerful enough to keep the voltage up for a couple of microseconds, maybe up to a milliseconds, to ensure that the write pending queue, the data in the write pending queue, can be written down to the media. So the upper part, this has to be controlled by the new CPU commands, and the lower part, this is done by the new motherboard design. Okay, here's the LSCPU command for the Cascade Lake. It's an 8240 CPU. You can see the size of the level 1, 2, and 3 cache. And here, Linux also knows the new CL flush and CL write back commands. Short comment, as far as I know, with the Cascade Lake generation, the CLWB is not implemented. It is mapped to CL flush, and the real implementation will come with a microcode update or with the next generation of Intel CPUs. Okay, so if you have this new application and the DCPMM below, of course the application can make use of this new CPU commands in a direct mode, because it's also part of the compiler suite, or you can make use of the non-volatile memory libraries. They are all open source under PMEM IO, PMDK, and they offer a bunch of different libraries. The libraries in red are also offering transactional logic behind. So just a short programming example. we have main, we are opening a file which is sitting in the system memory file system with a PMEM map file. The size should be 4 kilobyte. We are getting a virtual address space, and we can copy the system memory. We can copy data into this address space, and with this command we can ensure that it is really flushed to the media. And in case of the system memory, it will call a function PMEM persist, which will result in a CL flush. And if it's not sitting on the system memory, then it will be msync, which is the msync from the nmem command, which is the function we know already. And the PMEM unmap, this is sort of free. If we no longer need this address space, we can free it and give it back to the system. The example is also in the PMDK with a couple of other examples. The next portion is about a library called libart. It's implementing adaptive radix tree, which is used in databases where you want to insert a leaf in your tree, and the insert function, well, doesn't look too complicated. If you want to change this function into a transaction logic, then a couple of changes marked in red are needed. Just to give you an impression, if you want to protect each change with a transaction, and which would allow you also to run a rollback if something went wrong. So transactional logic is not really easy to implement with the persistent memory. But if you look back to today's storage, not every application needs in every piece of code this transactional logic so far. Okay, we have set up the device, we have got a short impression about the programming style and the programming models. So how about the performance, how about the measurements? As you have seen, there are already a couple of benchmarking tools around, but we said to ourselves when we want to create our own measurement tool, so we know what we are doing with the system, and we said, okay, we will grab and define different memory pools on the different CPUs. The memory pools will be divided in a couple of chunks, so that every thread will have its own chunk of data, and within this chunk of data we divide the chunk into blocks, and within the block we have the size of a cache line, so 64 bytes, and we are going, because we know that the access to the media is cache line granularity in 64 bytes. So if we only write a word of 8 bytes into a cache line, this would force the system to flush the complete cache line, because we wanted to increase heavy load. And these words can be written in a sequential mode or in a random mode. So this is basically the idea behind the program address test. And of course, we can start one or multiple threads on the system. Okay, and here's the disclaimer at the bottom. So all measurements have been done with a pre-production hardware. So this is not official benchmark, just to give you a first impression about the behavior. So the yellow line, this is the simulated PMEM, so this is DRAM basically. And the red, this is the early sample 2, which is an older version of the hardware, and the quality sample, this is already quite close to production, but still not the production ready. So I think you can expect that the production sample will be even a little bit better here in these lines. So the x-axis, this is the number of threads we used in parallel, and the y-axis, these are the CPU cycles needed for a single operation. So with a small number of threads, the performance between DRAM and persistent memory was really close, but when the load increases, then we saw quite a significant difference between DRAM and the system memory. So on the left-hand side is a sequential write of 4 kilobyte, and here we have a random write of a 4 kilobyte buffer. So as said before, this was our own example implementation, and by the way, the persistent memory, this was only one module, whereas in case of the DRAM, it was this group of 6 DRAM modules. Then in comparison, we used the official PM bench, which is part of the PMDK suite, and the same use case, we increased the number of threads with the x-axis, and now on y, it's not CPU cycles, but nanoseconds latency. But if you compare the two measurements, they are very similar. So our address test, as well as the PMEM bench with a moderate load, the performance is quite comparable. From a latency perspective, whereas under heavy load, we will see, especially with a random access, we will see quite a difference between the two media. Okay, just to remember the setup, we have the PMEM 0 with this interleaved configuration, the single module, and the PMEM 2 setting on the DRAM. And in the next pages, we used the MLC, which is coming from Intel, the memory latency checker. And here at the bottom, you can see the commands, the flags we used. So we wanted to measure the idle latency on all of our different file systems. And here is the nanoseconds, as you can see. DRAM, it's around about 80 nanoseconds, and the DCPMM is 170. And if I look at this chart, well, that's not too bad, isn't it? And it's also within the range Intel told us in January, where they expect a value between 100 and 350 nanoseconds. So the value on the left-hand side, this is if the measurement is done locally. So local means direct access to the CPU, and remote, this means access through the QPI from the second socket to the first socket where the reader is, and here the wave across the QPI will add approximately another 50 nanoseconds to the idle access. Okay, how about latency under heavy load measured with MLC? And again, you can see the command here. And in this command, a configuration file is used, and this is the line within this file. In the first parameter, it's the number of threads, which should be used from 1 to 40. It's a read access sequential with the PMEM logic and then the device behind. So yellow is the single DC PMM, the orange, this is the 2, and the green is the DRAM. And here you can see the bandwidth. So the best values are around about 6 or 8 threads. So one DCPMM will give you 7 gigabytes per second, 2 around about 14, and 6 DRAM modules will reach out to 60 gigabytes. So one DRAM provides you 10 gigabytes per second, one DCPMM around about 7 gigabytes per second. And again, this is not too bad. So the sequential read with the logic behind the reader head, this is really impressive to me. On the right hand side, the same stuff, just with not with a sequential, but with a random access.
What's that spike for?
So
Do you have an explanation for the spike?
Yes. Well, the spike, this is, well, well, the CPU has 24 cores.
Ah, right.
Okay, so all these threads are happening on the first core, and here it's the first time one or two threads will run on the second core. So again, you can see that there will be some caching effects be involved.
No hyperthreading. What's hyperthreading effect?
Turn off hyperthreading. See what happens.
You think this is about?
Yeah, of course.
Okay.
Of course it is. Because it's, by hyperthreading you're not getting more hardware. You're just adding, well, a logical CPU using the very same hardware.
Okay, I will check whether hyperthreading was active or not. So actually I cannot answer the question. So I thought we were switching to the second CPU, to the second socket here.
Ah, okay, that might. Maybe.
Okay.
So going across sockets can only be expensive,
Okay.
but that's pretty nasty.
Yeah. Okay. Well, that's true measurement. It's not fake. It's reality. Okay. So next page is about write, and again loaded latency, and the green is the memory, and up to 16 threads. It's very close from a loaded latency perspective, but of course I will get a different throughput, whether it's sitting on DRAM or on the system memory here. Yeah, so we have to recognize the latency. That's not an idle latency, it's a latency under load, under heavy load. And okay, this is the last example, which should demonstrate the change which is happening in the nmem libraries. So the example with the adaptive radix tree, the libart, which is also in the PMDK Git directory. So the numbers are the CPU cycles. Again, it's the DRAM, the older modules, the newer modules. And as you can see, with almost every version of PMDK, there was an increase in the performance. The number of CPU cycles were dropping down from 1.2, 1.3, 1.4. With DRAM, there was no improvement to 1.5, but still the PMDK benefited from the newer version. So for me, there is still lots of room for improvement in these libraries to speed up the usage if you want to access the PMDK at the persistent memory modules here. Well, in the last section, short outlook into the future, which might be interesting. And of course, if you have storage in your memory, you also want to see all features fulfilled with this new type of storage. And one feature is to get availability, high availability. So you want to store your data in your local server, but you also want to store it remotely in the second server. And yes, this is already also possible with a library called libpmem remote or RDMA PMEM. It might not be an optimal implementation now, but it's possible to run and test this, and this is called persistent memory over fabric. So we have NVMe over fabric, and upcoming is persistent memory over fabric. And again, I grabbed one page from the persistent memory fabric as the holy grail. Of course, if you think of shared storage today with the RAID systems and you have persistent memory, you can think of, I have two CPUs, a fabric in between, and I want to access a remote shared persistent memory. And there are a couple of new fabric technologies around, GenC, CCIX, OpenPARPI from IBM, and I think 2 weeks ago Intel announced also a new consortium, the Compute Express Link. And behind this, I think this was founded in 2016, 2017. And it will be interesting which technology will make it to enable such a remote shared persistent memory for us. So we have seen quite a couple of things are already possible and running, but there are also still a couple of open problems and issues. So first of all modules have the capabilities to be encrypted, and this is heavily recommended to encrypt the data, because you have to think of, you have now your main memory sitting on this data. And if you power off it, the main memory is still, the data of the main memory is still there. So if someone wants to look at your main memory, you can power off the machine, pull out the modules and try to look at the data. If you encrypt it, you are protected in such a way, but today you have to enter the passphrase during the boot command manually. So this is not a very convenient key management at the moment. There are changes ongoing in the Linux kernel, 5.0 maybe, 5.1, where such an unlock through a passphrase should be possible later on from the operating system. But at the moment it has to be done on the BIOS area. Then the number two, if you think of the applications which are making today use of the block interface, which are sitting on the block interface and looking for changes between the time T0 and T1. For example, if you want to replicate the modified blocks to a remote location, or from a virus scan perspective, if you want to only look at the blocks which have been modified, now the application will write directly to the persistency layer, not using the block interface. So actually you have no chance to monitor the changes in your system. Yeah, so this, for me, this is again unsolved, so, and we have to think about new solutions how to fix this issue for us. Or another interesting piece, today with this slow IOs, we have the convenience, if something goes wrong, the IO will come back with a -1. We can look at the error code, okay, there was a medium error, or a transport error or something, and the application can react and run a correction logic behind. Today, if the application uses a CPU command to store data, there is no return port to the CPU command, which could inform the application the store of the data went wrong. The only thing which will happen will be a machine check error, which will identify the DIMM module XY pattern serious error, and there is this EDAP, error detection and correction logic, in the Linux kernel, and this is already aware of this DCPMM. But at the moment, in the best case, you will get the information the module X failed with the physical address Y, but now you have the challenge to get back to the virtual address space to your application. Which application was using this physical address space? So again, it's not solved yet, and as I said already, a couple of more questions to be answered. But overall, yes, it's available now. Yesterday was the announcement from Intel at an attractive price. As far as I have read the messages yesterday, Intel did not disclose the price yet, but there was a statement 4 years ago at IDF from Diane. She was head of the data system group, and 4 years ago she said Intel target that the price will be half of DRAM, so let's assume this will come true, then for same price you can get a 64GB DRAM or 128 persistent memory. But if you want to get a price, please ask your provider of Fujitsu and we will make a proposal to you. So 4 times higher capacity, round about 10 times higher latency, as DRAM will be supported on all Fujitsu servers for Cascade Lake with /12 SP4 and /15 SP1. But with all the, let's say, the weaknesses we have observed so far, please keep in mind this is version 1 of a brand new technology. And if you go back 20 years ago to the fiber channel technology, version 1 of fiber channel had quite also some weaknesses, but over the next couple of years they evolved in terms of performance, stability, and I expect similar things to happen with this new technology. And on the second side, there are still a couple of issues and lots of room for improvement. So we have exciting days today, and especially with the shared memory, I expect to see more exciting years in the future with the persistent memory technology. So thank you very much for listening.